This is question number 6 and here it is given limit n tends to infinity of this pi k is equal to 2 to n of this is equal to dash. So pi k is equal to 2 to n. So this here this pi this is product notation. It indicates that all the terms of this sequence are multiplied, and so we'll find the answer. So limit n tends to infinity this. So we will so this is aq minus bq, k to the power 3 minus 1 to the power 3. So aq minus bq is equal to a minus b into a square plus ab plus b square. So this is aq plus bq. It will be a minus b into a square minus ab plus b square. So this is k minus 1 into k square. So uh, we applied here we will apply aq minus bq identity and aq plus bq identity. So by applying these identities we can get k minus 1. This is k minus 1 into k square plus k plus 1, and this is k plus 1 into k square minus k plus 1. So here we have to find out the limit of the limit n tends to infinity. So pi k is equal to 2 to n of this. So we will find what is the first term if we will substitute. This is it is starting from 2. So what is the first term of the sequence? So when we substitute 2, it will be 2 minus 1 into 2 square plus 2 plus 1. So 2 minus 1, what 2 minus 1 is equal to 1, and 2 plus 1 is equal to 3. So this is 1 by 3, this is 1 by 3, and this is 2 square plus 2 plus 1, that is 7, and 2 square 4 plus 2 is equal to 6 plus 7. So this is 2 square minus 2 plus 1 is equal to 2 square 4 minus 2 is equal to 2 plus 1 is equal to 3. This is 7 by 3. So similarly 3, the next number is 3. We'll substitute 3 here. So this is 3 minus 1 is equal to 3 minus 1 is equal to 2. So this is 2, and this is 3 plus 1 is equal to 4. 2 by 4 into. So this is k square plus 3 square 9 plus 3 is equal to 12. 12 plus 1 is equal to 13. So this is 3 square minus 3. 9 minus 3 is equal to 6. 6 plus 1 is equal to 7. So in this way you will find some terms some terms of this sequence. So I hope you understood this. Then we will observe the pattern among the among these numbers. So we will observe the pattern. You can see 7 is there as numerator and 7 is there as denominator. So the 7 will be cancelled here, and 13 is there numerator and 13 is there as denominator. So they will also be cancelled. 13 this 13 and this 13 will be cancelled. So we'll observe, we will see what is happening there. Okay, so you can observe this pattern, and you can observe this pattern by your own way, with your own way, and finally you will get the answer, that is 2 by 3. You can see um, you can see it here. Here 7 is there. Okay, so here 7 is there, and you will please see this is 7. Okay, so when you are moving, two steps, this is 7. Okay, this is one step, two step. So after moving two steps you are getting 7 as denominator. So this is 7 numerator and 7 denominator. So they are being cancelled, and then then you will see 3. So 3, so 3. Okay, you will find where 3. 3 is here, 3 is as and here 3 is denominator. So you have to find numerator 3. So move one step, two step, three step. Okay, so three after moving 3 steps, you will get 3 as denominator, 3 as numerator. Then 7 3 they are cancelled. Then is 2. So here 2 is as denominator. So you can see you cannot get 2 as new. Here 2 is as numerator. Here 2 is as numerator. So you cannot get 2 as denominator anywhere, because you can see all the denominators are greater than 2. Okay, so leave 2. Then go to 4. So this is 4, and you can see 4, and you have to move. Please see, this is first step, second step, third step, 4 steps. So after moving 4 steps, you could get 4 as numerator. Okay, so here these these two are cancelled. So here in case of 3 you moved 3 steps, and in case of 4, this is the denominator 3. In case of this denominator 3, you had to move 3 steps, and in case of this denominator 4, you had to move 4 steps. In case of 3, 3 steps. In case of 4, 4 steps. And in case of 7, let's see how many steps. Okay, in case of, okay, 7 has already cancelled here, 7 has already cancelled here. So you can see 13. So 13 is there. So 13 is the numerator. So in case of this numerator, you had to move 2 steps. So in case of this 13 is also a numerator, you have to move 1 step, 2 steps. So this is 13. Okay, so then the denominator 5, denominator 5. So here in case of denominator 3, you had to move 3 steps. In case of the denominator 5, in case of this denominator 4, you had to move 4 steps. And in case of this denominator 13, in case of this denominator 5, in case of this denominator 5, let's see, 1 step, 2 step, 3 step, 4 steps. Okay, so after 4 steps you are getting, after 4 after uh, after 4 steps you are getting. Okay, so you are getting 5. You are getting 5. Then you got 5. This is 5. This is 5 after 4 steps. Okay, after 4, after making 1 2 3 4, 4 steps you got 5. Then 21. So 21, this is numerator 21. So you have to go 2 steps. Okay, 1 2. So 2 steps. After moving 2 steps, after moving 2 steps, okay, you could get 21 as denominator. Then 6. So 6 is the numerator. 6 is the numerator. So 6 is the denominator. So you have to move, you have already known that you have to move either 3 or 4 steps to get 6 as numerator. Here 6 as denominator. You have already known that you have to move 3 or 4 steps to get 6 as numerator. So 1 2 3 4. After moving 4 steps, you got 6 as numerator. Okay, you got 6. This is 6 and this is 6. You got 6 as numerator. Okay, then 31. Okay, this is denominator, numerator 30, numerator 31. So after moving 2 steps, 1 step, this is 2 step. After moving 2 step, you are getting 31 as denominator. So they will be cancelled. The 7 is numerator. So 7 is a denominator. 7 is the denominator. So you have to move either 3 or 4 steps to get 7 as numerator. Okay, please go 7. Oh, this is 1, this is 2, this is 3. Okay, so after moving 3 steps, you have got 7 as denominator. So they will be cancelled. So 7 it is also cancelled. It we have cancelled it, so this is 7. So this is 43. So what is the numerator 43? We'll move, this is numerator 43. Then please move one step, two step. After moving two steps, this is numerator 43. After moving two steps, you got 43 as denominator, so it will be cancelled. So this is 8. 8 is numerator, denominator. 8 is denominator. This is denominator 8. So you have to search for a numerator 8. After moving 1 2 3 4 4 steps, you got numerator 8. Okay, so this is 9, this is 57, this is also 57. Okay. This is 57. This is 57, this is 57, and this is 9. There is also, you can see there is 9. Okay, this is 9. There is 9. Okay, so this is 73. This is also 73. You can see. Okay, this is 91. This is also 91, and this is 50. This is 57. This is 57. Okay, so you can see, if you observe it carefully, you can know, except 2 and 3, except 2 and 3, every numerator and every denominator will be cancelled. All numerators except 2 and 3, all numerators and denominators will be cancelled. So when you are you are going ahead, you can see, except 2 and 3, all numerators and denominators will be cancelled. So finally the answer is 2 by 3. You can observe this pattern carefully, uh, and so option B is true. We got option B is true. Then we'll come to this is 2 by 3, 2 by 3 is at option B, so option B is true. So then we'll go to question number 7. So which one of the following is true? Which one of the, you can see these are results, and you can see. So which one of the following is not true? It is asked there, which one of the following statement is not true? So you will see, every sequence of real number has a monotonic sequence. Yes, this is true. You have to find which one is not true. So the second is, every bounded sequence of real number has a convergent subsequence. This is also true. And every bounded sequence is convergent. This is not true. This statement is not true. And every convergent sequence is a Cauchy sequence. So this is also true. Actually, there are famous mathematical statements. Every Cauchy sequence is bounded. Every convergent sequence is Cauchy. Every convergent sequence is a Cauchy sequence, and a sequence is convergent if and only if and only if it is a Cauchy sequence. So there are every Cauchy sequence is bounded, but the converge is not true. These are very famous mathematical statements in real analysis. So you can see, every bounded every convergent sequence is bounded, but converge is not true. So every bounded sequence is convergent. So this is a false statement. All the, option A, option B, option D, these are true, but option C is not true. I have also explained by giving one example. So you can see this example. The false statement is, every bounded sequence is convergent. uh, so option B is true. You can see option, this is option C, sorry. Option C. Option C is true. Here you can see, okay, here you can see, because every bounded sequence may not or may not convergent sequence. Yes, every bounded sequence may or may not convergent sequence. We can give an example. We can see the sequence. It's a very famous sequence. N is equal to minus 1 to the power n, where n belongs to the set of natural number. So the elements of this set are minus 1 and 1. So clearly this set is a bounded set. This sequence is a bounded sequence, and this is a, you can see minus 1 is the greatest lower bound, and you can see minus 1 is the greatest lower bound and 1 is the lowest upper bound. So you can see this is a bounded sequence. This is a bounded sequence, but this is not convergent sequence. This is an oscillatory sequence because there are two limits. One is minus 1 and there is one limit points. The sequence minus 1 to the power n, I wrote it here. The sequence the sequence minus 1 to the power n, where n belongs to natural number, this sequence has two limit points, has limit points 1 and minus 1. So 1 and minus 1 are limit points. However, this sequence is not a convergent sequence. This is an oscillatory sequence. Actually, the definition of oscillatory sequence is limit superior. Limit superior. This is the sequence an. This is sequence n. Limit superior an. Limit superior. Um, the definition of oscillatory sequence is limit superior of an of the sequence. Limit superior is not equal to the limit inferior. You can see here the limit is inferior is minus 1 and limit superior is 1. So here minus 1 is not equal to 1. So in this sequence, limit superior is not equal to the limit inferior. So this is the definition of according to definition of oscillatory sequence. Limit superior a sequence is said to be an oscillatory sequence if limit superior of an is not equal to limit inferior of an. And the definition of divergent sequence is limit a sequence is said to be divergent sequence. A sequence an is said to be divergent. A sequence an is said to be divergent sequence if limit superior is equal to limit inferior is equal to plus infinity, or limit superior is equal to limit inferior is equal to minus infinity. A sequence is said to be divergent sequence if limit superior an limit superior an is equal to limit inferior an is equal to infinity, or limit superior an is equal to limit inferior an is equal to minus infinity. However, this sequence is not a convergent sequence, and it is a oscillator. It is an oscillatory sequence. So the sequence is bounded. It is bounded but not convergent. Bounded but not convergent. So here it is written every bounded sequence is convergent. But we got this example where the sequence is bounded but not convergent. So the option every bounded sequence is convergent, it is not true. So according to this question, so this question was asking which option is not true. So option C is not true, and so you can see option C is not true. Which is not true? Option C is not true. So option C is the answer. As option C is this is not true, so our answer is option C. Then we will go to question number 7. Question number 7. So it is asked there, limit n tends to infinity 1 by n into this is equal to dash. So here we will apply Cauchy's first theorem. So it is very Cauchy's first theorem of limit. This is a very famous theorem. So by Cauchy's fast theorem, limit n tends to infinity. You can see the definition and the theorem from your book. And by Cauchy's fast theorem, limit n tends to infinity. A n, the sequence is a n. The sequence is a n. A1 first term, second term, A2, A3, A4, A4. This is 4. This. Okay. So, by Cauchy's fast theorem, limit n tends to infinity. A1 plus A2 plus A3 plus A4 plus an plus dot 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 an uh, divided by n is equal to the limit of this. The limit of this will be equal to limit of this will be equal to limit of n. You can see limit n tends to infinity of this. This the limit n tends to infinity of this. This will be equal to the limit n will be equal to limit n tends to infinity an. So we can see. So this is n to the, you can see a1, because this is n to the power 1 by n. 1 to the power 1 by 1 is equal to 1. So this is 1. This is 2 to the power 1 by 2. 2 to the power 1 by 2. So this is a1. This is a2. This is a3. This is a4. Dot, 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 dot. This is uh, so this is n to the power 1 by n. So and this is by n, and this is whole divided by n. By n, it is there. So whole divided by n. This is also by n. So uh, it will be equal. It will be the limit of this total limit of this total sequence. This this is series actually. This is series. This is the sequence. This is n to the power 1 by n, 1 by n. This is a sequence, and this is a series. This total is this. This is n to the power 1 by n is equal to n. This is the sequence, and this is a1, a2, a1 plus a2 plus a3. This is the series, and to the power 1 by n. So however, limit n tends to infinity, this limit in n tends to infinity, this will be equal to limit n tends to infinity an, that is n to the power 1 by n. So limit n tends to infinity of this is equal to limit n tends to infinity n to the power 1 by n. We know that limit n tends to infinity n to the power 1 by n is equal to 1. So answer is 1. So option A is true. We can we, we can say limit n tends to infinity. This is equal to limit n tends to infinity n to the power 1 by n, that is 1. So option A is true. Then question number 9. So it is given, assume that there are an integer. So it is given there. Assume that there is an integer n0 such that n is lesser than or equal to n0. N is greater than or equal to n0, and the inequality an is greater than lesser than equal to bn holds. So this is an is a sequence, and bn is a sequence. Bn is the greater sequence. Bn an is a sequence. Bn is a sequence, and the sequence bn is greater than equal to the sequence an, or the sequence an is lesser than equal to the sequence bn holds. Which one of the following is true? It is given limit inferior an. Limit inferior of an is lesser than equal to limit inferior of bn, and four options are given. So when it is, can please see it carefully. So when there is an integer n0 such that n is greater than n is greater than n0, and the inequality an is lesser than vn holds, an is lesser than equal to vn holds, then we can say the limit inferior of an is lesser than equal to limit superior of an is lesser than equal to limit limit superior of an is lesser than equal to limit inferior of vn, and limit inferior of vn is lesser than equal to limit superior of vn. So by observing this, you can say this option is true. You can see this is limit an, and this is limit inferior an, this is limit inferior an, and this is limit inferior vn. So it is true that limit inferior of an is lesser than or equal to limit inferior of vn. So you can also observe how the other three options, b c d are not true. So option a is true. Then I will go to question number 10. Question number 10. So it is given limit n tends to infinity, 2 to the power minus 1 n square is equal to. So you will do it. Limit can do. Okay. So limit n tends to infinity, 2 to the power minus 1 into n square is equal to. So it will be n square by 2 to the power n. So 2 to the power n. Um, we this is 2 to the power minus n here, and it became 2 to the power plus n. So when we substitute infinity on the place of n, it will be infinity by infinity. This will be infinity by infinity form. So we will, according to L'Hospital rule, we will find this is the numerator, and this is numerator, this is denominator, and so this is numerator n square. We will find out the derivative of n square with respect to n. This is 2 to the power n, and we will find out the derivative of 2n with respect to n. So it will be 2n derivative 2n, and it is 2 to the power n ln 2. Again, if you'll see, if you'll substitute infinity on the place of n, again it is infinity by infinity form. Again we have to also find out the derivative of the numerator and of the denominator. So it is 2n. So and this is also infinity. This is infinity by infinity form. This is infinity by infinity form. So after finding out the derivative of 2n, it is 2, and this is 2 to the power n ln 2 whole square. So this is 2, and this is 2 to the power n. So when substitute infinity on the place of n, it will be 2 to the power infinity. This is 0. So 0 is the answer. So here option A. Here option A is true. You can say option A. Option A is true. So this question, this question number 10 was an easy question. So thank you so much.